The second video for section 2 talks a lot about what does it mean to be differentiable, what kind of statements can we prove are true and false from it, and what are some typical, maybe tricky questions that you should expect to see later on in this course. So just lots of different types of examples. We do have kind of a postulate or theorem, you could say, to start off the section. And it basically says that if you know something is differentiable, then it has to be continuous. Now this is written just at a certain point, but you could really kind of say this is true for the entire function. So if we have a certain value and we know it's differentiable there, a certain x value, it also has to be continuous. And if you go back to the previous three examples that we looked at, basically we said that if we have some sort of function, as long as it is kind of nice and smooth and curvy, it's going to be differentiable. That's maybe a summary of what we said. And anything that's smooth and curvy like that, it's going to be continuous. We'd have to look in our textbook to see if there's a proof for this or not, but I think it's something that makes sense. Now, what can we say from this? We're going to go back to geometry for a little bit and talk about a converse and a contrapositive. A converse is simply when you switch the if and then part. So we're going to do that and see if that same statement is true. And then we're also going to look at the contrapositive, which is when you switch things around but also add nots. And we're going to look at if that is true or not. So the converse to the statement in our box is that if f is continuous, then f is differentiable. And it's not true. Just to make sure you highlight that is not true. And you could simply look at the three previous examples. All of those were continuous, and they were not differentiable at certain spots. That's a very easy one to show that it is not true, and you just want to keep in mind that this does not mean that this would happen. Okay, let's look at the contrapositive. The contrapositive is if f is not continuous, then f is not differentiable. That is a true statement. Anytime you need to pick up your pencil to finish sketching the function, meaning it's not continuous, the derivatives also won't match up as you go from one to the other, and it's not going to be a nice smooth transition. You're not going to have a tangent line at that point. So that would be a true statement. In example 6, we're going to look at 4 different statements, and knowing that the function f is differentiable at x equals 2, we're going to basically explain why each of these things would also have to be true, why they each have to exist. This is going to be something that you might see on a multiple choice question, which one of these is true. It might be something that you actually have to prove, although that's kind of a rarer case, but it's a good thing for us to be able to think through a little bit. So remember, for all of these, f is differentiable at 2. So how do we know that each one of these following would also be true? First one is the limit as x approaches to a function f, just the fact that that exists. How do we know that that has to exist? So I should note that I'm not expecting you guys to come up with this on your own right now, but hopefully this will just get you thinking about some things. So because we know that the function is differentiable at 2, it also means it's continuous at 2. That's kind of the first step. And then if we go to our definition of what it means to be continuous at a certain point, that means that the limit as we get close to that certain point has to equal the actual value there. So because we know it's continuous, this statement has to be true. And remember, we're trying to show that this exists. Well, if it's equal to something else, it must exist. We're done. Okay, now it's tough, but that's kind of what we would go through as far as reasoning through it. You just need to maybe not be able to write this out formally, but again, for multiple choice, maybe just be able to recognize that, yeah, that would have to be around. Okay, part B. What does this whole thing, what does it really mean, and how can we show that it is actually true? You might be able to recognize that this is simply our difference quotient. What we have here is f of a plus h minus f of a. So our a value, the point that we're interested in, is x equals 2. It's all divided by h, and h is approaching 0. So really what this means is our difference quotient now is the same thing as our derivative at our a value, so the derivative at 2. And we're told that at 2 it is differentiable. We're told that that exists. So if this has to exist, that means that, written just a different way, that would also have to exist. Okay, part C. Does f of 2 have to exist? Well, basically, we're going to be doing the same thing as part A here. So because it's differentiable, it implies that it's continuous. And because we know it's continuous, we know that this part right up here, this statement here has to be true. The limit as we get close to that value has to actually equal the function value. And now instead of saying, well, the limit exists, now we're going to say that this exists. So for this one, we're just going to take this entire part right here and write it right down here. I'm not going to take the time to do that. And then from that, later on, we might say, oh, so f of 2 exists if we follow that same reasoning. Okay. Last part here. Let me see if I can zoom everything up. There we go. What does this last part mean? Look at it very carefully. Any connection that you can make. This one is very similar to part B. We're now using the alternative definition of a derivative. So what we have, this is f of x minus f of a over x minus a. I mean, they use c's, I guess. So f of x minus f of c over x minus c, and now it's the limit as x approaches c. So all the c's kind of match up. We have the x's and f of x's in the right spots. It's just our alternative definition. It's basically saying that this is f prime of 2. Okay, that's what that alternative definition is saying. So we're told that, again, just like part B, we're told that it exists in a different way, so just means the same exact thing. And our last example, this would be a typical multiple choice question. If we know that f is a function and we know that the limit as x approaches -3 of this quotient is if it's going to equal 2, which of the following has to be true? So pause it right now just to look at this based on what we've been talking about. Any idea how we could put this all together? Any ideas at all? So the first thing I look at anytime I see a fraction, I'm going to see if it matches up with one of our difference quotients. So here I'm noticing that x is approaching a number. It's not h approaching 0, so that leads me to believe the alternative definition might be in play. Here we see f of x minus f of that same value that x is approaching. And here's the tricky part. Instead of x minus a number, it's x plus 3, which is just like x minus a -3. So this all matches up with our alternative definition of a derivative, and they're saying that the derivative equals 2. The value that's here and kind of here, except it should be minus a -3, that's the x value that we're interested in. So this is really saying that f prime of -3 equals 2. At that point I might look through my options, or I might just look through them ahead of time, I don't know. But this one right here, the derivative of function f at -3 is 2. That's kind of what this is saying right here. So my answer for this would be option C. Last example says use your calculator. We are going to go through this in class, but just a heads up here, or just to note, all it is a tangent line. Find the tangent line of the function. And I am noticing, I'm not sure if this is on your notes or not. It is on your notes. Okay, so we're going to go through this in class later on.